For this question, we want to determine the input impedance, and we have 1, 2, 3, 4, 5 circuit elements. We've got 2 capacitors, 1 inductor, and 2 purely resistive elements. So since we're viewing the circuit from this side, what do we have? We have these 2 elements which are in series, then together they'll be in parallel to this one, then together they'll be in series with those 2 there. So how do we get the input impedance in this case? So firstly, since here we're dealing with AC, we have to change from the time domain to the phasor domain. That includes changing the inductors to impedance and the capacitors to impedance as well. So let's take Z1 to be the impedance due to the inductor, and Z2 the impedance due to this capacitor, and Z3 due to that capacitor. So how do you calculate impedance? For an inductor, we know that impedance is just J omega or J omega L, where L is the inductance, omega is the angular frequency. The angular frequency is given in the question. If there's a power source, we know to say to come with the angular frequency. So for Z1, we have J 8. So instead of angular frequency, which is 10 rads per second, multiplying 8. So this becomes J80. And of course, the units for impedance, ohms, same as resistance. Z2, that is a capacitor, so we have 1 over J omega C. So this will be equals to 1 over J by 10. The capacitance is 1 millifarads. So that's 1 by 1. That's 10 times 1 by 10 to the power minus 3. So just say times 1 times 10 to the power minus 3. This is the millifarad. So we've converted it to farads. So this is the 1 millifarads, but when you convert it to farads, it will show up like that. Okay, so when we simplify this, the 10 goes up, it becomes positive 10. So it's now, the 10 to the power negative 3 becomes positive, and that will be 1,000 over J10. This cancels with that, giving us 100 over J. Then when you multiply by J down and also by J in the numerator, basically rationalizing, you see that here you're going to end up with minus 1, and that gives our Z2 to be minus J100 ohms. In the same way, we get Z3, which is for a capacitor as well, so it will still be 1 over J omega C. So omega is still the same 10. The capacitance for this one also 1 millifarads, so also 1 by 10 to the minus 3. So we expect this to also reduce to minus J100 ohms. Once we have this, to now combine this to get the overall impedance, we know we have Z3 there in series with the 100 ohms, and then in series with the combination, the parallel combination of the Z2, this capacitor here. So that one will be in parallel with the series combination of Z1 plus 200. So I hope you've seen what I've done there. These 2 are in series, so they'll be added to account for this. Once they are combined, they'll be in parallel with Z2, so hence that. And then once you combine these together, now they'll be in series with those 2. So basically, this is what you have. So now we just have to find a way of combining these so that we can get the overall answer. So let's start by working out that part. So these 2 are in parallel. So Z3 first is just minus J100 plus 100 here. plus these two in parallel, so we'll have Z2. Z2 is minus J100. Since they're in parallel, we'll just multiply times Z1. Z1 is J80 plus 200. And then over the sum. So the sum will be minus J100 plus J80 plus 200. So this is minus J100 plus 100. When we multiply here, the first term times 100 there, that will be 8,000. J and J will give us minus 1, so the minus 1 will make this positive. Then next, the minus J100 will multiply the 200 there, giving a negative sign here. I comes here, so now we'll have 2 with 4 zeros. Over, in the denominator, we just have minus J100 plus J80 plus 200. We simplify in the brackets there. The numerator will remain the same for now. In the denominator, these two will subtract, leaving us with 200 minus J20. Now, since we want to end up combining this, we can, completely up to us here, we can choose to multiply this with a complex conjugate to just write it so that we get rid of that denominator. If we did that, we'd have to multiply this by 200 first. I think we're dealing with so many zeros, so let's try to cancel some of them. 20 can go into each term here. If we divided each term by 20, we have 8,000 divided by 20. We get 400 on the first term. And then here we get 1,000. Next, here we'll get 10. And then here we'll just remain with minus J. So now this side will multiply by 10 plus J over 10 plus J. Since in the denominator we'll have a difference of 2 squares, it will just be the first term squared, which is 10 squared, that will be 100, minus the second term squared, so minus J squared. J squared will be minus 1, giving us a plus 1 here. So still focusing on the last term there, the last part, the 400 will multiply 10 to give us 4,000. Then to multiply J to give us J400. And then the 1,000 to do the multiplication now have minus J 10,000. Then this will end up being plus. When the J and J gives us negative 1, it will be positive 1,000. In the denominator, we'll have 101. When you simplify that numerator, 4,000 and 1,000, that will give us 5,000. And then this will be minus, so we have 10,000 minus 400. So this will give us negative J9600 over 101. So we still have the rest of it. Don't forget, we still have this part. We're just focusing on the brackets. We've simplified so that now it looks like this. So here we can divide each term by 101 so that we have minus j 100 plus 100 plus 5000 divided by 101. So we get 49.5 minus, in the same way, we have 9600 divided by 101. We get J 95.05. So we simplify, these two are like, they all add up, we get 149.5, and then these two will also add up. So those two are also like, so we get minus J, that will be 195.05. So this becomes the overall impedance, and the units there is going to be in ohms. So this is the input impedance for our problem.